AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome back to AI for Climate Science. My name is Philip Stier from Oxford, and I will host a session today with Duncan Watson-Paris, who's no longer in Oxford, but is now at University of California in San Diego. But today we have not only one, but two exciting speakers, and I'll kick off with introducing Tom Beutler. He has a background in engineering and followed by a PhD in atmospheric science from MIT, and is now an assistant professor at the University of Lausanne, where he builds up a group at the intersection of atmospheric physics and machine learning. And with him today is our second speaker, Mary McGraw, who also has an engineering background and a PhD in atmospheric science, and is now a research scientist at Colorado State University and builds on a track record of atmospheric science and machine learning. And together, they will discuss the challenges and opportunities for the applications of AI for tropical meteorology. And I'm very much looking forward to this session. And I think kicking off today is Tom. Over to you.
Awesome. Thank you so much, Philip. Just as a quick check, can you see our slides and can you see and hear me properly?
We can see you, not yet your slides. We need the slides up.
Okay, let's try this.
Perfect.
Yeah, now you can see the slide. Okay, give me 1 second.
Yeah.
It's on the left. Yeah, perfect. Great. Well, I want to start by thanking Julien, Philip, Duncan, Martha, and more generally the AI for Good seminar series organizers for inviting us today. I really love this AI for Good webinar series, and it's an honor to participate along with Mary today. And as Philip said, it's a collaborative webinar today, and it's a really big collaborative webinar because we're not just presenting our own work today, but we're really giving an overview of some of our close collaborators' efforts. So we want to start by giving a huge thank you to our many contributors and collaborators. A lot of them are from Syria, Colorado State University, and participate in the AI to ES project, and a few of them are also from the University of Lausanne. And so without further ado, I'll get started. Today, we speaking about artificial intelligence and how it can benefit tropical meteorology. And I want to start with some definitions. So tropical meteorology can be broadly defined as a study of the tropical atmosphere. And so it tackles generally tropical circulations and systems, and that include tropical cyclones, the prediction of which will be a focus of today's presentation. So here you're seeing the evolution and the life cycle of Ian, which is a hurricane that formed last fall in the United States. And so there's no consensus on the unique definition of what a tropical cyclone is, but the definition we use in physics encompasses hurricanes, typhoons, tropical cyclones as a single physical phenomenon. And we usually define it as a rotating organized system of clouds. Clouds are condensed water that has a closed low-level circulation of air. And once tropical cyclones are mature enough, they have a distinct warm core, so they form a warm anomaly aloft, so above the surface, and that is one of the features that distinguishes them from extratropical storms that you may know as winter storms if you live in high latitudes. The intensity of tropical cyclones is usually discretized into categories, and these categories are based on the maximum sustained 10-meter wind speed. The exact definition depends on the regional prediction center, but these categories are usually used as proxy for the wind damage. And so below, I'm showing the Saffir-Simpson scale, which is used for hurricanes in the hurricanes or tropical cyclones in the North Atlantic and East Pacific. And you can see that for high categories, you have significant wind damage. But wind is only one of the different damages that a tropical cyclone can do. Actually, what the first cause of tropical cyclone-related death are flash floods and storm surge. And here's the footage of a storm surge triggered by Hurricane Ian last September when it made landfall next to Fort Myers in Florida. And it's easy to see here the devastating impact that it can have on human lives and infrastructure, etc. And so for that reason, we really care about accurately predicting the track and the intensity of tropical cyclones. And the traditional way of predicting them is using what we call dynamical forecasting. And in that setting, what we do is we integrate coupled dynamic and thermodynamic equations that represent the motion and different physical phenomena happening within the atmosphere. And we integrate them because we're on the Earth on a rotating sphere, and we integrate them forward in time to predict the weather. So as an example, I'm not going to go into the details, but I'm showing the equations that are integrated as part of the IFS, which is the model used by the European Center for Medium Range Forecast. So for those of you who are familiar with fluid dynamics, you can recognize the conservation of mass, of momentum, of temperature, of water vapor. And so a model like IFS will discretize these equations on the Earth grid. The most recent version uses finite elements as a discretization in the vertical and spectral discretization in the horizontal. But then more generally, you can just think of this as this is physical knowledge. We run it forward on the Earth, and then we get a prediction like this. And this is what we get using a tool called Windy to visualize the forecast made by ECMWF. And this is a forecast made for Tropical Cyclone Freddy. I pulled it yesterday, so this cyclone just passed southern Madagascar and is heading toward Mozambique. It's expected to make landfall on Friday or Saturday. Now, dynamical models, because they use a grid, are not designed to make accurate forecasts at the very local scale. And so that's why statistics come in. What statistics can do is they can use past observation to improve the prediction made by dynamical models. And so a classical example is what we call model output statistics. And these type of statistical model links the output of the dynamical forecast to observation using a statistical model. So to take the example of the forecast of Tropical Cyclone Freddy, if we start from a dynamical forecast, so we can start from the ECMWF1 or the American one made by the model called GFS, the statistical model, and that's really where machine learning which is a subclass of artificial intelligence models, comes in. So here I'm going to use, I like to use machine learning in the broadest sense. So that's any algorithm that learns to perform a task from data without being explicitly trained from that task. They can take the output of that dynamical forecast we just saw and then process it to improve it. And here I'm showing you an example using the FHLO system, and that was developed by Jonathan Lin based on a lot of work over many years by Kerry Emanuel and co-authors. And here we have the example of a hybrid forecast because it's using a statistical model, but also a physical model. And if you compare the image on the left and the image on the right, you can see that the statistical model allowed us to enrich that initial dynamical forecast. Now we have a full exceedance probability for when the winds are going to go above a certain threshold, which is really useful for risk assessment. And then if you look at the tracks, we started here from the American model. It's an ensemble model, so it already has several tracks, but now thanks to the statistical models, we have a lot more tracks. And so after introducing the statistical model, I'll hand over to Mary, which will discuss the challenges in the context of tropical meteorology.
Thanks, Tom. So as Tom just described, statistical forecasting can be a really excellent tool for weather prediction. However, there are some challenges of statistical forecasting, including AI forecasts, and these are specific to both meteorology and some of them specific to tropical meteorology. So one of the big challenges is that tropical cyclones are an extreme event. They don't happen very often. So that means that we're dealing with extreme events, and that also means we can have problems with quality and scarcity of our data. So as TCs are rare, they're rare in time and they're rare in space. Most places are not undergoing tropical cyclone conditions most of the time. Because they're both rare and they're violent, in situ observations can be really hard to get. So things like radio sondes that require you to fly an airplane into the tropical cyclone and measure things. We do that, but it's risky, it's expensive, and it doesn't give you a ton of data. And we do have radar, but if the tropical cyclone's not close enough to the radar to be seen, which is true in many places, especially the Southern Hemisphere in particular, it can be hard to get radar data. We do use satellite data to study tropical cyclones, but we can't always get the information we need at the right time, vertical and spatial scales. And especially if we're close to land, we really want information at a really high time frequency. The second big challenge is, again, if you recall a couple slides ago, Tom showed all those equations, the physics describing tropical cyclones. That's really complicated, highly nonlinear, really hard or impossible to solve analytically. So because the physics is so complicated, we have these complicated fluid dynamics and thermodynamics. We have to deal with rotation, the boundary layer, heat exchange between the air and the ocean, and so on. It can just be really hard to capture all of these processes accurately in a model. And even when we understand the processes physically, they can be hard to model numerically, like, for example, the Navier-Stokes equations. And there are some processes, like a lot of processes that have to do with lightning, cloud physics, et cetera, where we don't even necessarily understand the physics perfectly, let alone able to model them numerically. So yeah, so statistical forecasting is a useful tool, but there are some big challenges, and we're optimistic. We're hoping that machine learning can be a good tool to sort of address some of these challenges. So with that in mind, today we're going to talk about a couple of opportunities we see for using machine learning and artificial intelligence in tropical meteorology. And big picture, the two topics that we're going to focus on are improving the quality of our predictions of tropical cyclones and improving using machine learning to improve our understanding of the physics of tropical cyclones. So I'm going to walk us through this first topic, and then I'll hand it back to Tom for the second topic. So when I talk about improvement in prediction quality, I'm talking really about three specific topics today. Prediction of the formation of tropical cyclones, a process called tropical cyclogenesis, predicting the intensity and the track of a tropical cyclone once it's formed, and predicting rare events. And really what I'm going to focus on in this section is using machine learning to modify existing statistical forecast products. So can we take existing statistical forecasting tools that our experts already know, trust, and use, and can we improve on them with machine learning? And the hope is that if we start with something that we already trust and use and is in operations, we can sort of get any advantages brought by machine learning in the system more quickly. So with that in mind, we'll talk about tropical cyclone formation first, or tropical cyclogenesis. So we have existing statistical forecasts of tropical cyclogenesis. They're mostly based on linear algorithms like linear discriminant analysis. And these statistical products do provide skillful forecasts, but they can be limited. In particular, since they're predicting a rare event, often they suffer from false alarms. So too many false positives, which limits their utility. Recently, machine learning has been used successfully for very short-term forecasts or nowcasts of tropical cyclogenesis, but the success has been limited to very short timescales, so a couple of hours or less. So we want to focus on taking the existing statistical product, which can forecast tropical cyclogenesis on longer timescales, 6 to 12 hours out to a couple of days, and see if we can improve our skill with machine learning. And the second question we want to address with tropical cyclogenesis is how can we adapt and leverage machine learning models to better deal with rare events? So for our first question, we'll start by looking at this snapshot here of tropical cyclone activity on a day in September 2018. So you can see on this day, our existing algorithm identified 4 existing tropical cyclones in purple, 2 existing extratropical storms in pink, and an instance of tropical cyclogenesis in red. Now, if we look at the forecast made by the existing statistical model, a 6-hour forecast, so trying to predict this picture, we see that the existing model correctly identifies, hey, we've got existing storms here and here, and it does correctly identify the region of tropical cyclogenesis off Western Africa. However, it also flags 4 additional regions in the Pacific and the Indian Ocean as tropical cyclogenesis regions. When we look at the truth, we see there's nothing happening here. So we get some skill, but we have a lot of false positives. This summer, I worked with a summer student, Marshall Baldwin, and Chris Slocum of NOAA to replace this linear algorithm with a random forest algorithm. And when Marshall did that, he found that when the random forest algorithm made a 6-hour forecast of this picture, it had the same skill, so it was able to correctly identify existing storms and correctly identify the existing tropical cyclogenesis event. But the false alarms were greatly reduced. We still have this one over here in the Bay of Bengal, but none in the Pacific. So similar hit rate, way fewer false alarms. And Marshall extended these forecasts out to 12 hours. And again, his random forest algorithm was successful for 12-hour forecasts. And when he analyzed all of 2018 with this algorithm, he found that the random forest model had 56% fewer false alarms compared to the existing linear product and an almost identical hit rate. So we were able to maintain our existing skill and greatly reduce false alarms, which is a more useful product for forecasters. And currently we're working on extending this model to longer timescales. So the second problem is that tropical cyclogenesis is a rare event, and it's really hard to make skillful predictions of rare events. Tropical cyclones are forming less than 0.1% of the time. So we have an incredibly imbalanced data set, and we need to sort of adjust our machine learning approaches to deal with this data set. So traditional ways of handling class imbalance include strategies like oversampling, where we duplicate samples from our minority class to increase the sample size of the minority class. And we get to keep all of our data, which is nice, but we risk overfitting to a relatively small number of samples from our minority class. Another approach is undersampling, where we remove samples from our majority class to reduce the sample size of the majority class. And this way we reduce our likelihood of overfitting, but we are losing data. So we're throwing stuff away that could maybe be useful. There are other options out there as well that include creating synthetic examples and so on. So one of the downsides of these approaches is that we normally use them during model training. However, we can't rebalance the data when it comes time to test or run the model in real time, which means we have to make some adjustments to make things work in real time. And this can be difficult, especially when you have a data set as imbalanced as this one. Less than 1 in 1,000 of our samples will be our positive case. So as a way of addressing this problem, Milton Gomez, who's a PhD student at UNIL, University of Lausanne, developed a data-driven thresholding algorithm that rebalances the data before training. So this is a targeted undersampling algorithm. Milton's algorithm is a rule-based algorithm that optimizes a decision threshold for each feature. He creates a probability density function for each feature stratified by class and detects a thresholding criteria to rebalance the classes. And this has a few advantages. It's done before training, so it can be done the same way for training, testing, and real-time prediction. And it also gives us interpretable thresholds. So these thresholds provide rules that can make physical sense and that we can evaluate in the context of domain knowledge, which is really nice. So as an example, Milton's algorithm, the strongest rule that it created for this decision-based algorithm was based on sea surface temperature, or SST. This SST threshold detected by the algorithm basically discards data below a certain sea surface temperature. And we're able to, Milton is able to get rid of a percentage of his negative class, so rebalancing classes, while getting rid of virtually no positive class. And physically, this makes sense because people who study tropical cyclones know that it's very, very rare for a tropical cyclone to form in sea surface temperatures of less than 25 or 26 Celsius. So by getting rid of these samples with cold sea surface temperatures, we can work towards rebalancing classes. So after he applied his data-driven thresholding, Milton used the rebalanced data set to train a predictive tropical cyclogenesis model. And when he compared his data-driven filtering model, seen here in the red bars, to a predictive model of TC genesis with no filtering at all, seen here in gray, we see over here on the left that the model with data-driven filtering has a much higher positive predictive value than the model with no filter. Similarly, the existing statistical forecasts for tropical cyclogenesis has a brute force filter. So it does do some filtering, but it's very brute force. So when we compare the data-driven algorithm in red to the brute force algorithm in green, we see that the data-driven filtering algorithm has a higher hit rate. So basically, we have a lot fewer false positives with our data-driven filter by getting rid of some of our imbalance, which is an improvement over the unfiltered data, but we have a higher hit rate than if we used the brute force filter. So next, I'm going to talk about using machine learning to improve predictions of tropical cyclone intensity and track for existing storms. So as with tropical cyclogenesis, we have statistical forecasting models that make skillful forecasts of tropical cyclone intensity, and for intensity, our statistical forecasting models are approximately as good as the explicit numerical physics-based models. We also have statistical models for track. They're maybe not quite as good as the physics models, but they're still pretty useful and have some skill. And these statistical forecasts tend to be based on sort of background environmental conditions like winds, ocean, et cetera, and persistence. So what has the storm been doing over the past 12, 24, 36 hours? So the current algorithms take these relatively simple inputs and they use a simple statistical algorithm, often linear discriminant analysis, to make a prediction. Recently, we've seen studies use neural networks to classify tropical cyclone intensity based on satellite imagery, and this has been successful. So, excuse me, with that in mind, we're interested in a couple of things. We want to train skillful AI models for TC prediction based on existing statistical forecast products. And again, the advantage of using the existing framework is fast and computationally efficient, and a natural transition into operational forecasting because we're ingesting the same data. We're using the same predictors, the same features. And longer term, we hope to develop some explainable AI or XAI tools to provide additional interpretability to the experts using these AI models. So with that in mind, we have a second question, and that's because we know that for weather and climate predictions, we don't need just a central prediction. We also need uncertainty around our central prediction. That is, we don't just want to see our best guess. We also want to know the full range of possible forecasts beyond the best guess. So if you've ever seen the cone for hurricane forecasts, this gives us the full range of possible paths. It gives us our best guess in the center, shown by those black dots, and then the shading around it is the full range of possible places the hurricane could make landfall. And this uncertainty quantification is very, very important for decision-making for weather and climate predictions. If we have large uncertainty, that means we have low confidence in our predictions, which means a larger region needs to be prepared for possible really negative impacts. And even if we have high confidence in our prediction and relatively low uncertainty for something as high consequence as a hurricane landfall, hurricanes are some of the most expensive and dangerous disasters all over the world. So for something as high consequence as that, even 50 or 100 kilometers of uncertainty in exactly where the strongest winds will cross land can have massive consequences. So uncertainty quantification is really, really important for weather prediction. So one approach to incorporate uncertainty quantification into our AI models that's been explored and developed by Libby Barnes and Mark DeMaria at Colorado State and CIRA involves parametric distribution prediction. So that idea is training a neural network to predict a distribution rather than just a single deterministic value. So instead of outputting a single value, the neural network outputs the parameters of a probability distribution, such as mean, variance, skewness, and so on. And the distribution is conditioned on the parameters of the neural network. So it's very adaptable and flexible. So as I said, Libby Barnes and Mark DeMaria recently used this approach to predict tropical cyclone intensity. And they chose to model their intensity distribution with the hyperbolic sine arcsine distribution. You can read more about that in their paper. But the important thing is you can use whatever distribution best fits your data, but you do have to decide a priori. So you have to sort of choose an underlying distribution. So when they use this neural network model to forecast TC intensity distributions, this is what this looks like. So here's an example from Hurricane Ian, again, September of this past year. So these red, orange, yellow, and blue lines are the 1 to 5 day intensity forecasts made by the neural network model. The stars here indicate our truth, so the sort of best track forecast, which is what the hurricane actually did. So this was our actual maximum intensity. And the circles, the open circles, are what the NHC forecast was at this time. So sort of our expert knowledge, our best guess. And you can see that the neural network forecast captures both the truth and the expert guess, and it gives us the full range of possibilities. For some forecasts, the expert guess and the truth were really close together, like the 72-hour, the 24-hour forecast. But for other forecasts, like the 48-hour forecast, they were not so close together. So having this full distribution could be really, really useful for forecasters. And currently, this model has shown good skill at intensity forecasting when given cases over the past 10 years. So we're excited about this. And a similar approach can be used to make forecasts of tropical cyclone track, where we need uncertainty in two directions, both latitude and longitude. So again, we take a similar approach. This time, the data is modeled with a bivariate normal distribution. And over here on the right, again, we have a forecast of the track of Hurricane Ian with the ellipses showing error in both latitude and longitude, and the X's showing the truth, so where the center of the hurricane actually was. And again, we see that this neural network model is both skillful, the truth is pretty much always within our ellipses, even though it's kind of on the edge sometime. This was a pretty tricky forecast, so that's not surprising. And it's giving us good uncertainty. And for both of these models for track and intensity, the hope is that they'll undergo some real-time testing this hurricane season at the National Hurricane Center. So hopefully in the next year or two, we'll see AI models being incorporated into tropical cyclone forecasting, at least at the National Hurricane Center. And again, just as a side note, as I said before, uncertainty quantification is really important for weather and climate prediction. But it's important to note there's not a one-size-fits-all method. So I just talked about one method, this parametric distributional prediction, where we predict a PDF. But there are a lot of other ways to quantify uncertainty with your AI models. You can use ensemble prediction. You can use non-parametric prediction like quantile regression, or newer methods for weather and climate like Bayesian neural networks. But the important thing is that for an AI model to be useful for weather and climate prediction, it needs to give not just a central prediction, but uncertainty. So that's really key. So finally, our last topic in this section is predicting rare events. And we're actually really using machine learning to predict a rare event of a rare event, since tropical cyclones are already rare. So the rare event that I'll show you next is rapid intensification, which really just refers to big changes in tropical cyclone wind speeds in short periods of time. So the tropical cyclone is getting really strong really quickly. We have an existing statistical model that's used to forecast rapid intensification. You can see that here in gray. And this model is skillful, but particularly at higher probabilities of rapid intensification, it starts to lose some skill and it tends to under forecast. And that's really bad. We really don't like under forecasting or misses in weather prediction. So we're above this 1-to-1 line. When we train a random forest model seen here in blue on the exact same data as our statistical model in gray, we see improvement in forecasting, especially at this higher probability, in these higher probability events. And now we're slightly over forecasting, which is better than under forecasting. When we add our machine learning model into the existing consensus, we get this pink line, which is pretty close to the 1-to-1 line. So it definitely improves our ability to forecast these rare events, again, especially at these higher probability events. We've also seen success in using convolutional neural networks trained on satellite data to forecast rapid intensification. This study was carried out by a group at SIMS in Madison, Wisconsin. And again, we see, especially for higher probability events, the CNN model shown here in gray is really, really useful. And we've also seen, there's also another random forest model being developed by Chris Slocum at NOAA. Okay, so to wrap it up, machine learning models can make skillful TC forecasts with uncertainty. AI-based models can be used for successful predictions of tropical cyclone intensity and track. And we can design these models to include uncertainty in their predictions, which is really important for weather and climate. We have also seen some skill at AI-based models in predicting extreme events like rapid intensification. And all of these models are hopefully going to at some point undergo the research to operations process so that they can be used operationally and actually play a role in improving real-time weather forecasts. And with that, I'm going to hand it back to Tom to talk about machine learning and tropical cyclone physics.
Yeah, thank you, Mary. That was a fantastic overview, and it's so exciting that some of these products are going to make it to operation soon. Hopefully. Fingers crossed.
Yeah.
So I'm going to talk about, in the second part, how machine learning can also facilitate our understanding of tropical cyclone physics. And rather than just a one-way interaction, I really want to frame it as a two-way interaction between data, so observational or high-fidelity model data, and the physical knowledge we have in tropical meteorology. So what I want to start with is going from the left side to the right-hand side, which is how can we use machine learning to extract knowledge, ideally new knowledge from data, which you can refer to as data-driven discovery. And that's a question I think, at least I often get is, okay, are we at the stage where we really are learning something new? Have you ever learned new physics from artificial intelligence? And my answer is always the same. It takes time. It takes time because we're building on a large body of physical knowledge, and because we first need to position ourselves at the state of the art when it comes to the physical problem we're addressing. And so, as an example, I want to show the work of Frédéric Tam, who is a PhD student at the University of Lausanne. And again, we trying to challenge state-of-the-art question, and one of the questions that recently emerged is whether cloud radiative feedback have a critical role in how tropical cyclones intensify, and if they do, what exactly their role is. And so to demonstrate that this feedback is critical and that has already been established for just a couple of years, I'm showing two different simulations with the exact same model, HWRF, which is a high-resolution weather forecasting model that is used operationally. So the advantage is we can work on very realistic simulation. And on the left is a control simulation of tropical cyclone Haiyan. And what you can see is that the tropical cyclone will form. Here we're showing the magnitude of the maximum surface winds. And on the right, so James Rupert ran this simulation. He created an artificial world where he artificially suppressed cloud radiative feedback. And so from these movies I showed initially, you probably noticed how visible the cloud tops are. And these clouds can trap thermal radiation emitted from the Earth and different layer of the atmosphere, and how this, what we call long wave or thermal radiation, interacts with water vapor, clouds, and circulation, can positively feedback. And it's believed to be critical to the early intensification of tropical cyclones. But now it has been identified as critical, but we don't know exactly how it acts. And so the question we ask here is, what exact spatial patterns of radiative heating, so we not only looking at thermal radiation, but also solar radiation, promote or prevent the intensification of tropical cyclones? And for that, we have designed, or I should say Frédéric has adapted principal component regression to make it as transparent as possible. And that way, he can extract, ideally, new physical knowledge from data. And I'm going to show you some of his preliminary results, which I think are quite exciting. And so the way he does it is that he starts from realistic tropical cyclone experiment. In that case of Typhoon Haiyan, which made it to category 5, so it was really exceptionally intense. And then a question we always have is, how do we go from a full 4-dimensional field to something we can process? And in some of the modern machine learning architectures that have been already talked about in this webinar series, you can learn from data how to optimally compress the data. But I think we heard from Mary, a constant challenge in tropical meteorology is we just don't have that many samples. And so in that case, we will choose how we reduce the dimensionality, and we'll do it using principal component analysis. And here we design it really generally so that we can disentangle different physical mechanisms. So you can process any field using principal component analysis and go from 4-dimensional time series, 4-dimensional fields to time series of the component explaining most of the variability. And then, and that's where the idea of building transparent machine learning models come in. So transparent machine learning is machine learning that we don't need to interpret post hoc. We build it so that we can already directly extract knowledge from it. So what we do is we're going to linearly combine each input feature, in this case, the different loadings from the principal component analysis, into separate optimal structure. And for interpretability reason, we keep one structure per variable. And then once we have projected the original signal, the full field on these structures, we can use any regression model we want. So this can be multiple linear regression, artificial neural networks. We can tailor it to the data at hand. And then we can predict the quantity we're interested in. Here we're interested in tropical cyclone intensification, and we're going to keep it simple. We're going to go from radiative heating, because that's what we're interested in, to how tropical cyclones intensify. So we're going to learn a simple mapping from thermal and solar radiation to surface tropical cyclone intensification. And I can already show you the results we get, and I'll show you what we get in the very simple linear case. We can extract from data the three-dimensional spatial structure most relevant to intensification. So we can extract that from these optimal patterns. Not only that, but also quantify exactly how it contributes to TC intensification. So this is the kind of structure we get, and unlike previous physical frameworks where you have to either make stationarity assumptions or assume that average the tropical cyclones azimuthally and not get the full details of how the TC asymmetries, and in that case, the asymmetries in radiative heating amplify the tropical cyclones. Here we can really get the full structure, and you can see we have a nice asymmetry here at the mid-levels. We do it for thermal radiation, we do it for shortwave radiation, and the framework not only allows us to get this optimal structure, but also the full equation. So here we learned a transfer function from the heating we get from radiation to the intensification. So we know that the intensification is related to how long wave project on this structure and short wave project on this structure. And from these coefficients, we can play really fun games. So we can, for example, know the kind of radiative fields that will double the intensification of the tropical cyclone. So with that, we hope to establish firm physical knowledge of here a difficult problem, how a different physical mechanism, in this case, radiative heating, can influence the intensification of tropical cyclones. So this is an example of using machine learning to extract knowledge from data. But now this interaction can go two-way, and we do have a lot of robust physical knowledge in atmospheric science and in tropical meteorology. And so we can use that physical knowledge to constrain the outputs of a machine learning algorithms to make more robust predictions. And so key motivation is some work I've done in the context of climate modeling, where we've shown that by physically rescaling the inputs of a neural networks to transform a difficult extrapolation problem into an easier interpolation problem, we can create models of storms and cloud inside a climate model that can generalize even when environmental conditions greatly change. And so to show that, we put ourselves in several different climate models and designed this really difficult generalization setting where we train and validate model on a cold, in that case, aquaplanet, but also here I'm showing Earth-like simulation. And then we test the model in a simulation whose surface was warmed by 8 Kelvin. So that's a brutal warming, which we hope to never observe, but it's a good test for the limits of our physical models. And if we just do that with standard neural networks, they fail to generalize. If we rescale their inputs, they manage to much better generalize. We go from an error of a factor 5 to 10 to an error that's really small and we're happy with. And I want to go in a little more in the details of how we did that to understand how we can then take this method and apply it to tropical meteorology. And so the input that is most problematic in this climate modeling and global warming context is actually related to water vapor. Because as you increase temperature linearly, because of the Clausius-Clapeyron equation, the amount of water vapor that a given air mass can contain before it condenses into liquid water will increase near exponentially. And that's why if I look at the logarithm of the histogram of specific humidity and compare it from the cold to the warm climate, in the 8 Kelvin warmer climate, we reach values that we've never seen in the cold climate, and that causes extrapolation errors for machine learning algorithms. But now we know the Clausius-Clapeyron equation, so we can rescale specific humidity to relative humidity. And now you can see that these two distributions align much better. And they don't need to perfectly align. All we want is for them to have a similar support so that you're not in an extrapolation situation when you're in the warmer climate. And we've shown in the context, again, of subgrid scale parameterization for climate modeling that such a physical rescaling greatly improves the generalization ability of machine learning algorithms. And so here I'm showing the coefficient of determination, which measures the error of a neural network model. Without and with the rescaling, 1 is perfect, is a perfect model. 0 means the error is as large as standard deviation, and you can go all the way down to -infinity because we're looking at the coefficient of determination, which is different from the coefficient of correlation. And you can see that here for mid-tropospheric subgrid heating, we really managed to fix most of the generalization error. And so with Mary, and that's why she came here to Switzerland, we've been designing a really fun project of how to take these kind of ideas to tropical meteorology. And so the motivation is that physical knowledge can make machine learning more robust, which means that the prediction quality of our machine learning algorithms would not decrease as long as the data has reasonable variations. But these variations can be large, like we are expecting with global warming for the thermodynamic environment. And so for tropical cyclones, the question we were really interested in is, can potential intensity theory, which links the large-scale thermodynamic environment to the maximal velocity that can be attained within a tropical cyclone, help us create robust prediction algorithms that can generalize across very different environmental conditions? And I don't have time to fully go into potential intensity theory, but I'll give you a quick primer. The idea, and that came from a seminal paper in the 80s, is to make an analogy between the tropical cyclones and Carnot engines and think about their thermodynamic efficiency. So by balancing two terms, the heat and the moisture that tropical cyclones extract from the ocean and the work they have to do to go against the surface friction of the ocean and keep spinning, by balancing these two terms, you can derive an upper bound for the maximum winds. And this upper bound depends on here an efficiency term that's linked to the surface temperature and the temperature in the outflow of the hurricane, a ratio of the enthalpy and the momentum exchange coefficient, which is still a topic of active research. I've linked a review here, and the near surface enthalpy disequilibrium, which drives, which tells you how much energy you can extract from the ocean. So this paper has been revised several times by the original author and several groups, and now there's a more recent derivation that makes less assumption, which we always like from a machine learning perspective, because we don't want to put too many assumptions on the data. And you can recalculate this quantity from the difference in convective available potential energy between the ascending parcels near the eye wall and the descending parcels that are driven by radiative subsidence. Okay, taking a few steps back, if you don't know too many if you don't know all the thermodynamics, what you can think of is just from the knowledge of the environment, you can tell that the winds in the tropical cyclones are not going to exceed a certain bound. And now that we know that bound, we can use it to rescale the output of a machine learning prediction model. So instead of just predicting intensity, we're going to predict intensity divided by the upper bound that we know from physics. And our hope is that because this upper bound can adapt to different temperature, moisture, energy conditions, it can help us generalize across seasons, basins, or climate. And as preliminary results, I'm going to show you similar distributions as I showed you before, but this time it's not the input we're looking at, it's the output we're looking at. And so here I'm showing the intensity in knots. And so you can divide by 2 to get the intensity in meter per second, roughly. You can see here the logarithm of the distribution of intensity. And for example, if we were to train the machine learning intensity prediction model using southern hemispheric case, it would struggle to generalize to the East Pacific because it would have to guess all these higher values that are never seen in the training set. Whereas if we scale the intensity, now the support of the East Pacific scaled intensity distribution lies within the support of the scaled intensity distribution in the Southern Hemisphere. And so now we know we're going to be much closer to an interpolation case, which statistical models can handle. And our preliminary results show that we can use the scaled intensity in the prediction without hurting too much the prediction. And right now we're working on testing different generalization cases. Okay, but now a common criticism of physically informed or physically guided machine learning is that we don't have physical knowledge of every single phenomenon in the atmosphere. A lot of time it's very complicated. So what do we do when we don't have such physical knowledge? And that's why in our group and in other groups, there's a lot of active research on how to best combine tools from causal inference and tools from machine learning. And the combination referred to as causal machine learning can help remove spurious links or correlations without degrading performance. The idea is that you can take you to the time series in your training data, and then from the analysis of these time series, you can use different definitions of causality. In our case, we're going to use the PC stable and PC MCI algorithms from the Tigromite library developed by Jakob Runger and co-authors. The library is open, it's very user-friendly. And what it does is from this time series, it can estimate the most likely causal links. And most importantly, for our case, eliminate spurious associations. And so imagine we start from a null hypothesis, which is sometimes what we do in machine learning, that all inputs are relevant to predicting the output. We can take that as the initial condition. So we say, okay, if I start with the initial gates that all of my inputs, all of my data are relevant, then can I use these causal discovery algorithms to select which links are spurious and eliminate them, and therefore end up with much less inputs and a much more parsimonious models that has eliminated most of these spurious correlations. And then in the results I'm going to show you applied to, again, the prediction of tropical cyclones, we're using a really exciting, newly developed multi-data version of these algorithms that can take several multivariate time series, so in our case, several tropical cyclone cases, and output a single causal graph. And that's the work of Andreas Gerhardus, who's a postdoc at the DLR working with Jakob Runger. And so in the case of tropical cyclone prediction, we can use these causal discovery algorithms to select the optimal set of predictors. And so we kind of going to take a kitchen sink approach because we didn't want to, again, we want to put as little a priori assumptions as possible. And so we're going to throw in all the meteorological variables that we, I mean, not only the ones that we think are relevant, but all the ones that are readily available in the data set we're looking at all the different vertical levels in different horizontal sectors at all time lags, and that will define as a feature. And then the goal of the causal machine learning algorithm is to select the features that lead to robust predictions. So here's a non-exclusive list of the meteorological variables we considered: horizontal divergence, vertical velocity, vorticity, humidity, geopotential, potential temperature, wind shear, and various column integrals. You can see that we're really trying here to make as little assumptions as possible and to learn the optimal drivers from data. And so for that, after reducing the dimensionality of our inputs, what we do is we feed them through these multi-data PC stable or PC MCI algorithms. And then the goal of these algorithms is to eliminate as many spurious links as possible, depending on their hyperparameters. And once we are left with the set of causal predictors, we can use them to drive any machine learning models. So here you have the choice: multiple linear regression, random forest, artificial neural network, etc. And then we target tropical cyclone intensity variables. In that case, we're going to mostly focus on what we traditionally call intensity, which is the maximum sustained surface wind speed, but we also have results on minimum sea level pressure and precipitation. So then what Sharanya did is to carefully set aside a few tropical cyclone cases, in this case 50 cases, to really test what we hope to bring with causal inference, which is a model that can generalize much better, because it hasn't just learned on the correlations of the training set, it has learned a more general relationship akin to what we're trying to do when we derive physical models. And this is the results we got that got us really enthusiastic about the results. So here we varying the hyperparameter, determining how many inputs get selected by the causal discovery algorithms. And we're getting this very reassuring curve for the training set that the more inputs we use, the better our prediction, and that we expect. However, what we hope is that the first inputs that are selected by the causal discovery algorithms are more relevant than when it uses all of them. And so we get, thank you. We get the really nice looking curve here where we have an optimal range. And so here we have the best validation performance on these tropical cyclones we set aside for the first causal predictor selected by the causal discovery algorithm. And we show in a paper that has been accepted for publication in the proceedings of the Climate Informatics Conference, we're currently revising it and we'll make the preprint available after that, that this multi-data causal feature selection, so causal feature selection method refers to a way of selecting inputs, outperforms selecting inputs at random based on XAI. We took the example of a random forest, or select based on lag correlation, which is a common way of doing it. And now going back to the physics that we can learn, I think that's what we're going to use. We're going to compare the inputs selected by the lagged correlation-based feature selection method with what we get from the causal method. And here what we see is that the correlation-based method focuses on variables that highly correlate with surface intensity, and they're at the very edge of the prediction window. So it's just going to try to find variables that are as close as possible to the to the surface intensity we're trying to predict. And so in this case, it really focuses on vertical velocity, whereas the causal algorithm can pick variables at earlier time lags, and so really developed a general model about the environmental conditions that are favorable for intensification. And here we see it's focused a lot on the divergence, which is reassuring from a physical perspective, because it's directly linked to the steering flow and also to the adjustment between the primary and the secondary circulation. And it also puts relative humidity in the inner core on top, which we expect from physical knowledge. And with that, I'll hand it over. So in conclusion, I hope to convince us there's a real fruitful two-way interaction between data and physical knowledge that is facilitated by machine learning.
Okay, so we're just about done here, but before we open it up to questions and answers, we've talked about ongoing work using machine learning to improve TC prediction and to improve our physical understanding of tropical cyclones. And we just want to leave you with a couple of sort of looking ahead to areas where we think there's growth or things to be aware of when it comes to machine learning and tropical meteorology. So the first thing is this idea of using machine learning to create additional data sets to study tropical meteorology. So for TC forecasting, we use satellite imagery, and we have visible and infrared satellite products like those from GOES and Himawari that give us high temporal coverage. We get new updates out every 10 minutes, but these instruments can't really see through the clouds. So we only get sort of a snapshot of what's going on the top. Microwave instruments can see through the clouds. They can give us a lot more information about the vertical structure of tropical cyclones, but these instruments are on polar orbiting satellites, which only pass over a location about every 12 hours. So even if we include all available microwave images, we're only getting updates of a given location every 3 hours. So a team at CIRA is really interested in, can we use a neural network trained on this high time frequency visible in IR imagery to sort of fill in the gaps in our microwave imagery? So can we use machine learning to sort of almost interpolate this microwave satellite imagery? And we hope not only will this be useful for forecasting, but also for understanding physics, particularly sort of 3D physics that really benefit from being able to see through the cloud, because 3 hours with weather forecasting, a lot can happen in 3 hours, especially if you're looking at high impact events. And so this video was given to me by Kathy Haynes at CIRA, and she and Chris Slocum have really led a team that's shown some promising early results using GOES inputs shown here in orange and sort of our microwave observations shown in blue to, again, fill in these gaps with our microwave coverage. And you can see their neural network-based results are down here at the bottom. And we're pretty excited about this and hoping to get some exciting results in the next couple of years. The second thing to be aware of when talking about AI is bias. And we know that AI can be subject to many biases. And when we use AI and machine learning models, we need to be aware of those. And in particular, what those biases look like for earth science problems. So there are several different kinds of bias, systemic or structural, human, statistical, and data bias. All of these kinds of bias influence and drive each other. In earth science, what this often looks like, so systemic bias can be things like lower quality of historical data before satellites, or the fact that rich neighborhoods often have higher quality forecasts. Statistical or computational bias is the bias that sort of exists in our algorithms, and also the fact that ultimately humans are applying these algorithms, so can't remove humans from the equation. And AI can be biased by ignorance of the laws of physics, so really important to develop physics-aware models like the ones that Tom just talked about. Data bias includes things like selection bias, so you can't study it if you don't include it in your model. Or interpretation bias, which again is influenced by humans sort of seeing what they expect to see, and data pre-processing choices, which sometimes we can use them to reduce bias, but they can often introduce additional biases of their own. And when you're dealing with rare events, there's also inherent bias if you don't have a big enough sample size. And finally, there's the human factor, which again is present in all of these other factors as well. And it includes things like our tendency to see patterns, even if there aren't any, our sort of limitations on how much information we as humans can process at once. So people like weather forecasters, especially when you're working under pressure, and also the impacts of groups. Groups can act to mitigate bias with diverse viewpoints, but they can be subject to groupthink as well. So again, just things to keep in mind anytime we're working with AI. And I think on that note, Tom is going to close with one more thing we're excited about with AI and tropical meteorology.
So it's really nice to have Mary, who's a member of AI2ES, which I think has really led a lot of reflection on the ethical biases that can be a pitfall for artificial intelligence, even in earth sciences, even if now that's a really important topic. And so I think that what that shows is and I hope we convince you that the potential of artificial intelligence for tropical meteorology is clear because of these biases, but also because every paper tends to establish their results on slightly different data sets and slightly different performance metrics. We quite hindered by the lack of unified training data and evaluation protocols. And the way the machine learning community has been tackling such problem is by introducing benchmark data sets. So famous benchmark data sets include MNIST, CIFAR, ImageNet, and more recently they have permeated weather and climate science with WeatherBench. The several benchmark data sets proposed by Maelstrom and data sets related to climate projections such as Climate Bench. And so with Mary, but also multiple partners from different university and regional prediction centers, we all agreed would be really helpful to start a benchmark data set for tropical cyclone prediction. Oops. And then, sorry, there's been Oh, and so we thought such a benchmark data set could provide AI-ready data sets for TC prediction at different timescales, and we collaboratively listed a few a few targets and evaluation protocols. And our hope is really that we design evaluation protocols with enough tropical meteorologists that machine learning practitioner can just take this platform and this data set, providing not just data, but also scoring functions that can be directly used to produce results that are relevant to operations and relevant to the community without having to spend dozens of years catching up on all the domain knowledge. And with that, I want to thank you for the invitation, and we are happy to take any question. Thank you.
Fantastic. Thank you both so much. It's great to have that overview of use of machine learning in tropical meteorology and covering a huge range of different topics. And it's great to see all the different research that's going on, particularly starting to think about and explore using it operationally. There are a few questions in the chat, so I'll start with a question from Peter Watson. I had a similar question myself. He asks, Marie, it's cool to apply machine learning to improve tropical cyclone track forecasts, but have any particular tests been done for edge cases where machine learning might struggle more? For example, TCs with intensities beyond any seen in training. He says this seems to be necessary for operational use where prediction errors could be dangerous.
Yeah, that's a great question, Peter. Thanks for that. And I think one of the things that Tom and I are excited about with this sort of physically scaled intensity is we think that that is a way to sort of better address some of these edge cases, because you're right. One of the things that's really scary is that a machine learning model, you don't always know how it's going to perform on sort of extreme or out of sample data. I think another thing, again, other ways to address this include, including the uncertainty quantification, I think also helps with that. And then, so we have done case studies, which is sort of the traditional meteorologist way of evaluating. So I know that, for example, Ian was a really tricky forecast. So running back and looking at, especially when we know sort of like how or why the forecast was bad, I think looking at a case study, especially in conjunction with these XAI, like the interpretability tools, which is not something we've been able to do yet, but hopefully in the next couple of months, that is coming. I think sort of knowing if we got it right, did we get it right for the right reasons? If we got it wrong, did we get it wrong for the wrong reasons? And so on. So hopefully that answered your question. And yeah, that's a great question.
Yeah, no, I think you're right, and it's an exciting use of Tom's invariance work. I wondered, you mentioned about the predictions for Ian and the uncertainty estimates that you provide or are predicting. Have you considered or explored using or trying to account for model uncertainty? And I guess there's two types of model uncertainty, right? There's there's uncertainty in the physical model, but then there's also kind of a structural or architectural uncertainty in the ML model.
It's like I paid you to ask me about one of my favorite topics. Yeah, so we've been thinking about that, especially at my group at CIRA. We've been thinking about that a lot. So sort of the uncertainty within the model and the uncertainty within the data itself. And that's it's challenging, but it's difficult. So I know that that's actually like a big topic of current research. I know that one of the advantages of Bayesian neural networks is the idea that you can sort of decompose that uncertainty into what's coming from the data and what's coming from the model. But the downside of Bayesian neural networks in particular is they can be very expensive to run, and you can run into a lot of memory problems. So there's a group at the National Center for Atmospheric Research in Boulder, led by David John Gagne, that's also working quite a bit on this. And of course, it's 6 p.m. here in Switzerland, so I'm blanking on the exact name of what they call, I think it's like evidential neural networks, I believe is, I just saw a presentation on this like a month ago, and it's really cool and interesting. But yeah, they're working on ways to sort of decompose the uncertainty into, what's coming from the model, which can hopefully maybe be targeted and reduced, and what's coming from the data, which is a lot harder to reduce, at least without greatly increasing the amount of data you're ingesting, which is not always possible. So yeah, I think I could talk about just that for like a whole hour, but
no, that was great.
I spared you.
Wouldn't get the
That was
hour.
a good answer. Thank you.
Maybe a question to both of you, and that's a really it's in a way a cheap question, but I think it's particularly relevant in this context. I mean, with tropical cyclones being such a rare event, but such a high impact event, what do you think about the public perception if it goes wrong, if it's a black box model as such? Is it a bigger problem than anything else? Because it's, in this case, the impact couldn't be bigger, and people see this only once in their lifetime.
Do you want to start?
Oh, I can start. Yeah, I mean, I think the answer was almost in the question, because the event is so impactful. You really want a model that's as interpretable as possible, especially because we in a case in tropical meteorology where we have very little samples. So you want the uncertainty to be properly quantified, and since it's a high impact decision, you want to exactly understand why you make your decision. So that's why I believe, and I think we'll hear what Mary thinks, but given her work, I think she's been using models that are adapted to the number of samples that we have. So a lot of these algorithms we presented today are simple, right? Random forest, principal component regression, and that's because I wouldn't feel comfortable having a neural network that, even if you don't quite measure that it's going to overfit, will probably overfit on that new tropical cyclone case you haven't seen before, and then you have to use post hoc explainable tools. We'd rather create models that are directly interpretable by construction, and that's what we call transparent machine learning. And that's what's so important for me, at least as we design model. And I think that's where the physical knowledge that we use to create the models is also really important, because it facilitates interpretability, especially by meteorologists, which are often have a very strong physical training.
Yeah, and I would just add to what Tom said. I think the existing physics-based models, as far the meteorologists and the forecasters understand how they work, but I think they're pretty black boxy to the general public too. I don't know that we do a particularly good job of explaining to the general public how a numerical weather prediction model works. So in that sense, I actually don't know that an AI model is like a whole lot worse than all of these. And we have black boxes in the NWP models, right? All of our like parameterizations and cloud physics. So that's not to say that we shouldn't strive for transparent AI, like Tom was saying, but just I think there are a lot of ways that we could improve our communication with the general public. And also, to what Tom was saying, one of the things in our transition to operations in particular, we really do value and look at that forecaster impact, because they can be really picky about, they have really high standards for like, I want to understand why this thing is telling me what it's telling me. So I think sort of involving them throughout the process and getting their feedback and sort of saying, what is the information you need to make this AI model useful to you, is really important. Because if you've ever been on a forecasting floor, they're looking at like 8 different screens at once, and things are updating every 30 seconds. And it's just, there's a lot going on. So we need to work with them to make sure that we're giving them and the decision makers the information they need, not just what we think they need.
Thanks. Yes. Good answer.
I have a slightly more technical question for Tom, actually. So I really like this approach where you are looking at the radiative effect on tropical cyclogenesis, and you used forgive me and correct me if I'm wrong, did you use PCA to do the dimensionality reduction before doing the linear regression?
Yes, so we use PCA, yes, correct.
So obviously with the, the linearity gives you interpretability and allows you to then do this kind of reconstruction afterwards and decompose the different competing effects of shortwave and longwave. I guess though it relies on, it can only be as accurate as linear as the system is. How do you account for, could you account for nonlinearities in the dimensionality reduction step? Or do you feel does the model do pretty well? Forgive me if I missed it in the talk, but are you able to capture the intensification pretty accurately just with a linear model? Is it really that simple?
Yeah, no, so that's a great question. So the way we set it up is that once we use a dimensionality reduction step to get the patterns that give us the most predictability, then the model we put after that can be linear or nonlinear. Okay. And so we did make tests where we went from these optimal patterns, then added an artificial neural network and tested, the number of, as we increase the number of layer, can you learn more and more nonlinear relationships? We didn't want to give up on the interpretability of the framework, so we still combined the signal into patterns. That being said, you can add the number of patterns to have more and more flexible inputs, but then the regression model itself can be as nonlinear as you wish. And in this particular case, we didn't really gain anything from adding nonlinearity. So we stuck with a linear model, but the advantage is that you can put any kind of nonlinear model afterwards. And the way we set it up is even if you have a nonlinear model, you can still extract the most relevant patterns. And so but it does make assumptions in how we make the dimension, how we reduce the dimensionality. Yeah. And that's something we would address with a more general encoder had we enough data, which we don't in this particular case.
No, there's an interesting interplay, isn't there, between the dimensionality reduction step and then the regression. I also wanted to ask you about the PCMCI. So I completely buy the argument and using these to try and reduce the number of predictors, particularly where you have so many potential choices. Is there a risk though potentially that you're learning the physics from a physical model that is itself not perfect, right? And you're kind of, are you looking at applying these to observations to learn the observed physics as well?
So in that case, we applied it to reanalysis, meteorological reanalysis, in the case of tropical cyclones, which is already one step towards observations. So we're really happy, and in that case, it works very well. And so there's nothing that would prevent us from going one step further and completely used, what people would call purely observational products, although there's often a little model at some point. But yeah, we want to progress more and more towards, for example, remote sensing data, etc. So yeah, no, to answer your question, I think that's a nice thing is that also, unlike other machine learning approach, these causal machine learning approaches are not too data greedy, and when you're working with real observations, you're often data limited. So we're quite optimistic that we can apply them to observational data sets. And I also want to say, sadly, I'm going to have to step out, but Mary is going to stay, so she can take all the other questions. Thank you so much, Mary.
Yeah, I'll do my best to impersonate Tom.
No, I already have one last question anyway, and then we can wrap up. And naturally, this one was for you anyway, and it follows on nicely from the reanalysis that Tom mentioned, and you mentioned. I was really excited to see this data filling approach right at the end, where you're looking to combine GOES and microwave data. How does that fit in with, obviously at NCAR you have this huge data assimilation framework. How does this kind of fit in with that and those existing tools? And have you kind of thought about what that looks like operationally yet, or is it still very kind of bleeding edge?
Oh boy, yeah, that is, I think, probably a ways down the road. And also, I am a new member of the. I was not involved with developing that product. I'm hopefully going to get to start looking at it to do some tropical cyclone science. But yeah, and I think the nuts and bolts of incorporating that data into operational forecasting is, I'm not the person to ask about that. I do think with such a big project like that, I think we are sort of going to, I think it is going to be a bit of a process, like demonstrating that this is trustworthy. So trustworthiness is a thing that we talk about a lot. I'm part of the NSF AI Institute, and trustworthiness is a thing we talk about a lot. Like, how do you get your end user to trust your data and your model? And I think with this sort of simulated, when you say like simulated data to a forecaster, I think their antenna goes up a little, and it should. It's good. It's good for them to be really discerning. So I think one of the things we've been talking about a lot, and that I think will take some time, is this trustworthiness thing, is getting the end users to feel comfortable and confident that we're giving them good information. And yeah, and I think in the meantime, those of us who don't have to actually make life and death forecasts and just get to do fun math and science can hopefully get some new physics out of it. But yeah, that's definitely, and I think with a lot of AI products, one of the reasons that I spent so much time focusing on our sort of really simple models is because those almost have this built-in trustworthiness, because they're built into these existing products. So the forecasters, when you can tell them everything's the same, but we changed the statistical equation, now it's a random forest algorithm, that's like usually a little bit easier to work with in a lot of ways. They feel like, okay, I only have to learn one new thing. And it's also just sort of from the information technology infrastructure, it's a little bit easier for them to work with it. So that's kind of why we spend so much time on these kind of simple things, is because when it comes to actually using these to hopefully save money, save lives, save property, we can kind of get there a little faster if we're only teaching, or if we're only focusing on one change rather than like, here's a whole giant new thing and you have to start from scratch.
Makes sense. That's very sensible. Brilliant. Well, I think that just leaves us to thank you both again for a really interesting talk and, as I say, a fascinating oversight of all of the different areas of research that you're both doing. The virtual applause going on in the background. And I think I'd hand it over to the ITU to have our closeout. But we look forward to seeing the audience again
and on behalf of Tom, thanks for having us. We had a lot of fun putting this talk together, and please feel free to reach out with further questions or ideas. Thanks so much.
Thank you.
Great. Thanks a lot. It was great.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
you.